Hi student. The next topic is properties of a colloidal solution. The colloidal solution having the different properties like colligative properties, Tyndall effect, color, Brownian moment, charge on the colloidal particle, electrophoresis, and coagulation or precipitation. First we will discuss the colligative properties. What are colligative properties? I will recall that colligative properties. Already we were studying solution lesson. Just I recall that properties depends on the number of solute particles irrespective of their nature relative, that is nature relative to the total number of the particle present in the solution, that is called the colligative properties. Here the number of particles, see the colloidal particles being aggregates, the number of particles in the colloidal solution is comparatively small as compared to the true solution. Okay, these are colligative properties. Like osmotic pressure, elevation of boiling point, then depression of freezing point, and last one is osmotic pressure. These are called colligative properties. Already we discussed this. And the next one is Tyndall effect. Tyndall effect I will tell you later. Then third one is color. What is the color? The properties of the colloidal solution, color of the nature. The colloidal solution depends on the wavelength of the light skirted by the dispersed particle. That is, the wavelength of light further depends on the size and the nature of the particle. Usually, size and the depends on the size and the nature of the particle. The color of the colloidal solution also also changes with the manner in which the observers, that is receives of the light. For examples, milk and water, that is mixture of milk and water. If you see the reflected light and transmitted when you see the water and milk, that is mixture of water and milk, when you see that in reflected light, means what, that appearance is blue. That is, when you viewed with the transmitted light, that appearance is red. So in reflected light, blue in color, in transmitted light, red in color. Okay, this is the color of nature. That is properties of the colloidal solution. When you see in reflected light, that colors appears in blue, transmitted light red. Why? Because means that depends on the wavelength of the light that is scattered by the dispersed particle, so that the wavelength is differ, so that the color also differ. Okay, then the Brownian moment. It is very important one. The Brownian moment. Suppose the colloidal solution, if you see in under a powerful ultra microscope means ultra microscope. The ultra microscope, the colloidal particles usually appears to be zigzag, that is the continuous zigzag motion. So that's been all over the field of the solution, all over the field of studies. The motion, usually the zigzag motion, independent of the nature. This is independent of the nature. That's mean that but this is independent of the nature, but depends on the size of the particle and viscosity of the solution. That's mean smaller the size, suppose the Brownian moment, the smaller the size and lesser the viscosity, that's mean faster the motion. In case bigger the size, higher the viscosity, slower the motion, like an oil and water in a colloidal solution. So any liquid colloidal solution, suppose you pour in one beaker to another beaker, the viscosity is lesser, so that what happens, it's immediately the transfer is the motion is faster. Suppose higher the viscosity means, for example oil, the motion is slow. Okay, this is called a Brownian moment. then charge on the colloidal particles. See, the colloidal particles always carries a charge. That is, the nature of the charge is the same on the colloidal particle given a colloidal solution. That may be either positive or negatively charged. Some positively charged and negatively charged salts I will tell you. See, the properties of colloidal salt, there is two types. That is, one is positively charged salt and negatively charged salt. Here given the positively charged salt is hydrated metallic oxide is Al2O3XH2O, CrO3XH2O, FeO3XH2O. These are the called hydrated metallic oxide. That is the example. And metals like this is having a negatively charged salt like copper, gold, silver, so etc. These are the negatively charged salt. And the second is basic dyestuff like methylene blue is a positively charged salt. Here the metallic sulfide, is arsenous sulfide, antimonous sulfide, and cadmium sulfide salt. These are the negatively charged salt. And the third one is hemoglobin, that is in blood, positively charged salt. The negatively charged salt is acid dyestuff. Then that is called eosin, Congo red, like this. Eosin, Congo red salt. These are the negatively charged salt. And fourth one is oxide like titanium dioxide salt. This is our positively charged salt. And here the salt of starch, gum, gelatin, clay, charcoal. These are the negatively charged salt. Suppose that the charge on the salt particles is due to the one or more reason, like what are that means, due to the electron capture. Because of the positive or negative charge means due to the electron captured by salt particles during the electrodepressions of the metal. That is due to the preferential adsorption of ion from the solution, or due to the formulation of the electrical double layer. First you must know that electrical double layer. What are electrical double layer means? That is, they have two layers. One is a diffused layer, another one is fixed layer. That is called the electrical double layer. So the preferential adsorption, usually the preferential adsorption of ion is the most accepted region for the salt. The salt particles acquire positive or negative charge by preferential adsorption. That is, the positive or negative ion. When the two or more ions are present in the dispersion medium, that is, the salt present in the dispersion medium, means negatively charged colloidal solution results. So that I will tell you that one example. When you add that silver nitrate and AgNO3 and Ki, potassium iodide solution. Suppose if I add that silver nitrate solution added to potassium iodide, the silver nitrate solution added to potassium iodide, the precipitated of silver iodide adsorbs iodide ion. So the precipitated of silver iodide adsorbs iodide ion. That is, they forms a dispersion medium and negatively charged colloidal substance. That is, the negatively charged colloidal solution results. So that if suppose if I add potassium iodide to AgNO3, silver nitrate, the positively charged are result. Here the negatively charged salts are result. That means AgI, that is negative. So that this is negatively charged salt. Suppose I add here potassium iodide to AgNO3, means positively charged salt are here. Ag plus, this is positively charged salt. In case the second example, this is in the dispersion medium. See, this is in the dispersion medium. This is very important. Then if I add FeCl3, ferric chloride added to excess of hot water, the positively charged salts of hydrated ferric ion oxides formed due to absorption of Fe3 plus ion, like Fe2O3XH2O, means that is, here the Fe3 plus ion absorbed the dispersion medium, so that it will be positively charged salt. In case the ferric chloride added to NaOH, FeO3 H2O to result in OH minus ion. That is the adsorption only that OH hydroxide ion. So that this is called negatively charged salt. Negatively charged salt. So this is the combination of that. That's mean the positive and negative charge. See, they forms a layer. That is the electrical double layer. That layer attracts the counter ion from the medium, forming the second layer. So that they forms one is diffused layer, another one is fixed layer. That is called electrical double layer. Usually that combination of the two layer opposite charge, there is one is positive and negative charge around the colloidal particle is called Helmholtz electrical double layer. Helmholtz electrical double layer. That is the Helmholtz electrical double layer. That is one is diffused layer, another one is fixed layer. Diffused layer, another one is fixed layer. So the potential difference of between the fixed layer and the diffused layer, the potential difference between the fixed layer and the diffused layer of opposite charge is called zeta potential or electrokinetic potential. Zeta potential or electrokinetic potential. So the next is electrophoresis. So electrophoresis, the apparatus setup. And this is the apparatus setup. So one is anode and next one is cathode. This is a reservoir. This is reservoir and this is a colloidal solution. Colloidal solution, and this is the water level. That is the initial level. This is initial level of the colloidal solution. Then this water level. That is the dispersion medium. Here the water level is a dispersion medium. Water is a dispersion medium under this stopcock. And see, this is the setup of the electrophoresis experiment. See, the electrophoresis means the existence of charge on the colloidal particle. Charge on the colloidal particle is confirmed by the electrophoresis experiment. See that when electric potential is applied across to platinum electrode dipping in a colloidal solution. So dipping in a colloidal solution, the colloidal particles move towards one or other electrode. So from this electrode to and this electrode. So movements of this particle. So movements of the charged particle. The movement of the colloidal particle under an applied electric potential is called electrophoresis. The key word is electrophoresis means the movement of the colloidal particles under an applied electric field is called electrophoresis. So the positively charged particles move towards the cathode. See, the positively charged particles move towards the cathode end. So while the negatively charged particles move towards the anode. Negatively charged particles move towards the anode. So this is the experimental setup. See, when electrophoresis, that is the movement of the particles, the prevented by some suitable, mean that is it observed that the dispersion medium. So water, here dispersion medium is what? Water. So observed that the dispersion medium begins to move electric field. So this phenomenon is called electroosmosis. This phenomenon is called electroosmosis. The next is the last one. That is coagulation or precipitation. Coagulation or precipitation. See, what is meant by the coagulation? See, the stability of the hydrophobic salt due to the presence of the charge on the colloidal particle. See, somehow the charge removed by the particles near each other form aggregates or coagulate and settle down. So under the force of the gravity. Okay, so the process of setting a colloidal particle is called coagulation or precipitation. Precipitation of the salt. The process of setting of colloidal particle is called coagulation or precipitation of the salt. See, this coagulation of lyophilic salt can be explained by the some term, like by electrophoresis. Electrophoresis, by mixing of two oppositely charged salt, mixing of two oppositely charged salt, boiling by boiling persistent dialysis by persistent dialysis by addition of electrolyte So these are the methods, that is the classification way. So first one, the electrophoresis. By electrophoresis, by electrophoresis, the colloidal particles movement towards the oppositely charged electrodes get discharged and precipitated. So by electrophoresis method, oppositely to, that is colloidal particles move towards oppositely charged electrodes, so get discharged and precipitated like this. Then second is by mixing two oppositely charged salt. By mixing two oppositely charged salt. By mixing of the opposite charged salt. See, the oppositely charged salt when mixed in almost equal proportion, mainly they neutralize their charge and get partially or completely precipitated. Either partially or completely precipitated. For example, mixing of the hydrated ion, like hydrated ferric oxide, that is positively salt, and arsenious sulfide is a negatively salt. So bring them into the precipitate form. So this type of coagulation is called mutual coagulation. This type of coagulation is called mutual coagulation. Mutual coagulation. The next is by boiling. By boiling, when the salt is boiled, the adsorbed layer is disturbed. So the adsorbed layer is disturbed due to the increased collision with the molecules of a dispersion medium, so that it reduces the charge on the particles and ultimately lead to the settle down, that is settling down in the form of a precipitated. Then by persistent dialysis, on prolonged dialysis, that is traces of the electrolyte present in the salt are removed almost completely, and the colloids become unstable and ultimately coagulate. Here this is called persistent dialysis. Then by addition of electrolyte, this is Hardy-Seckel's rule, that is addition of electrolyte. When excess of electrolyte is added, what happens? The colloidal particles are precipitated. So the reason is that the colloid interact with the ions carrying the charge opposite to the present themselves. That means they cause neutralization leading to their coagulation. The ion responsible for the neutralization of charge on the particles. So this is called coagulation of ion. So negative ion causes the precipitation of positively charged salt and vice versa. The opposite one is vice versa. So usually it is observed when it's greater the valence of the flow clothing, The flow clothing means nothing but the collecting of the particle. This is called flow clothing, the collecting of the particle. The flow clothing ion is added, the greater the power cause precipitation. So this is called Hardy-Seckel's rule. Very important, Hardy-Seckel's rule. So I repeat this: greater the valence of the flow clothing ions are added, the greater its power. So cause precipitating. This is called Hardy-Seckel's rule. So in this coagulation, negative salt, the flow clothing power is, order is like this. Like Al3 plus is greater than Ba 2 plus is greater than sodium plus Na plus. Okay, so this is the order. So similarly, the coagulation of positive charge, flow clotting power, positive charge and this is for negative. So this is for negative. For positive, positive charge the order is complex and Fe Cn 6 times 4 minus is greater than phosphate PO4 3 minus is greater than SO4 2 minus greater than Cl minus. Okay, this is the flow clotting power, that is the Hardy-Sacker's rule for negatively charges and positively charges are. Okay. Then coagulation of the lyophilic salt and protection of the colloids. This is the coagulation of the lyophilic salt. See, the lyophilic salt, two factors are there. That is the charge and the solvation of the colloidal particle. The two factors, charge and solvation of the colloidal particles. When the two factors are removed, that is charge and colloidal particle, the lyophilic salt can be coagulated by adding electrolyte and adding suitable solvent. First one is adding electrolyte and suitable solvent. When solvent such alcohol and acetones are added to hydrophilic salt, the dehydration of dispersed phases occur. Okay? Under this condition, the small quantity of electrolyte can be bring about the coagulation. So then protection of colloids. The protection of colloids are, that is, more stable than the lyophobic salt. This due to the main fact that lyophilic colloids are extensively solvated, that is, the colloidal particles are covered by a liquid which they are dispersed. Okay, sheath of the liquid in which they are dispersed. Okay, the lyophilic colloids have a unique property of protecting lyophobic colloids, because when a lyophilic salt is added to the lyophobic salt, the lyophilic particles form a layer around the lyophobic particles. So thus the product later from the electrolyte. So that lyophilic colloids used to this purpose and called protective colloid. This is called protective colloids. Okay, the last one is Tyndall effect. The next one so next one is this emulsion. Okay, we will discuss the Tyndall effect in next session.